several different shapes that these are going to make. And it depends on the structure of the equation for what shape it's going to be. So the very first thing we're going to do is we're going to kind of decode what shape is which. These are not things we need to memorize. We're only going to work them when we can look at stuff. So don't like try and memorize these. We don't need to. But we're going to have ways of making circles. And circles are going to look like a number times cosine equals theta. So our equations are going to be written pretty much as r equals. So circles are going to look like this. And when we have our two different circles, if we have one with a cosine, oh, hang on, I need to make that pen skinnier. There we go. We're going to wind up with the radius on the x-axis. And if we have a circle equation given to us with a sine, we're going to have the radius on the y-axis. So if we had, and we saw this yesterday, r equals a number, that has our center right at the origin. So these ones are not going to have the center on the origin. It's going to be a little bit off. But it's either going to be on the x-axis or on the y-axis. We can't just have free floating circles. And an important thing that we're going to need to know about circles is they have a period, so a length of pi. We are going to be working polar graphs pretty much exclusively in radians. So everything's going to be in terms of radians. And circles look like circles. We know what circles look like.
Draw it so we can make sure.
Ooh. I know, I'm so good at art. I'm good at drawing things. So then we're going to look at our next piece, which is called a Limacon, is how that's pronounced. I'll write it out. I'm going to zoom it in super close so I can write. So this is a Limacon. That's how you say that. Limacon. I genuinely am okay if you say that. I do not care. I think technically it has like a weird accent on that C. I think if you read it properly, it's got like one of those doodads in there. But
That's crazy.
I didn't do foreign languages all that much, so I don't remember. And Limacons just means we're going to have a number plus something cosine theta, or something minus something cosine theta, or sine. And these have a couple of different ways they're going to look, and we're going to see that as we start graphing. Sometimes they're going to look kind of like a pinched circle, where it looks kind of like a fat heart. Sometimes they're going to be like a little loop-de-loop inside a circle. And they could be facing up, they could be facing to the side. It could be like that. So they're making a weird loop-de-loop. And with Limacons, an important thing we need to have is we need to have the period length on this. These have a period of 2 pi. So these, we will have to fill in a whole table. Oh my gosh. There we go. My bracelets keep half turning in my iPad. So our third one up here is called a rose. And roses don't have any pluses or minuses in them. It's just a number. But they do have another one inside here with our theta. So roses look kind of like, if you think cartoon flower, like think daisy, like those guys, or it might be like this. I'm gonna say, well, we're gonna see ones like that. We have two different actual lengths of periods on here because n is a super important piece on this. If we look at this n that's gonna be inside either one of them, if n is even, the period is 2 pi. And there are 2 times n petals. And when we say petals, I mean, I'm gonna start grabbing the color. That's a petal. Or that's a petal.
Are they called roses because it looks like a flower?
Because it looks like a flower.
So is that like not an English word? I don't know.
What do you mean?
Like, I'm assuming that most of math languages are Greek, so why is it roses? Is roses not an English word?
I genuinely do not know the etymology of the word rose.
Too advanced into historical analysis.
Okay.
You're heading into lit stuff, and I'm like, I'm not an English teacher. I don't know.
Being from English, I understand, but leave that shit.
Stuff. All right, so then if n is odd, so we have a different option here. Because if n is even, we have a period of 2 pi. If n is odd, we're going to have a period of just pi. And there are n petals. So it doesn't duplicate itself. And we will see these. We will graph them. I was gonna say, super close. So we have another one that has a weird type of name. And this one, I'm zooming it in so I can write it down so we can say it. These are Keats. Think Keats. Lemnis Keats. Again, Latin's weird, math is annoying. We go with that. So Lemnis Keats look like an infinity sign. They can be diagonal, so they can go on an angle, but they look kind of like an infinity. And they have, looking at their equations, squares. They're the only ones that are going to have squares here. And lemniscates have a period of pi. And then our last one is called a spiral of Archimedes. And I was like, Archimedes, really, really old guy, did a whole lot of inventing in math. But back in the day when we, just had adding and subtracting. And so spiral of Archimedes is one of the only ones that does not have a trig function in it. There's no sine, there's no cosine.
Oh, yeah.
And so the spiral of Archimedes, shock of all shocks, looks like a spiral.
So it's like a spider web, like direct.
Well, isn't there like a natural
Spiral.
sensation that's like a spiral that you see like a spiral?
And that would be called the Archimedes spiral. It's part of the golden ratio. That is that's the same Archimedes. And the spiral of Archimedes have no period. They are infinite.
Oh, yeah.
The song you say you're gonna save me your place. I'm fighting. You should listen to
Okay, so these are our 5 different types of equations we have. So the reason we care about the period on these is think about our unit circle and how we can keep going around and around and around, and we'd find all those coterminal angles. So every place on these trig functions where we have coterminal angles, it repeats. So these all become pathways that just go around and around and around and around. So everything that has a period length is something that is cyclic. It is periodic. It is repetitious. The spiral starts small and just gets bigger and bigger. It just keeps going out and out and out and out. So what we're going to start with down at the bottom is we're just going to figure out which shape it is, and then we'll start doing our graphing. So we're not going to actually do any solving or anything with those guys at the bottom. We're going to look and see, what are they? What would these look like? So we're going to play matchy up with the top. So let's look at number 1 down here. What shape is this one going to be? The lemnisketes, because it's got the r squared. How about number 2? What's that one going to be? Spiral of Archimedes, because it does not have a trig function. They should be right at the bottom of that page. This is that full page that we were working on right here.
Nerd.
All right, so then let's look at number 3. I was gonna say, hang on, this one has a number inside with our trig functions. So there's very little difference between the circle, which is a number, and then cosine theta, versus a number cosine number theta. So this guy is a rose. Limacons. It feels very French. I'm with you. All right, so let's look number 4. What do we think for number 4? Yeah, the one that looks like lima bean. Limason.
Excuse me?
I was like, if you are one of those foreign language like accenty persons, the accent thingy looks like that, I think, or it's hard to read them, I think, or it's more like that. One of those things that is not a foreign language I took, so I don't know what those are or what they're called. It's a thing.
Oh yeah.
It's a squiggly, but Google does not like the squigglies, so I don't know how they are, and I can also barely see them on the little thing that I have that has it with the phonetic pronunciation. Yeah, so it's kind of, it's a thing. I do not care if you have the accent on there. Like, genuinely, I don't care. Valid. I don't know. Some. I'm gonna go with Latin. I think Latin. I think it exists in many things. I did not go high enough in French then to see this. Or I paid none attention to my accents. Also true. Son. It makes a All right, let's look at number 5. What do you think number 5 is going to be? Spiral. Because it doesn't have a trig function. How about number 6? Circle. That one's going to be a circle 1. Because we don't have a number inside the trig function. So look between the difference between 3 and 6.
Roses.
So 3 is a rose, 6 is a circle.
Roses are red.
So 7 we think is a rose. How about 8?
Circle.
Circle. Are we good? Why? And number 9 is a limason. I am not going to police pronunciation on those. They're weird.
So if I say limacon as
I don't care if you call it a lima bean.
What if I call it a rose?
Okay, then I do care. Because then it's just wrong. Pronunciation I don't care with. Don't be wrong. I don't care if you call it a lima bean and a lemon cat. I don't care. because lemon skeets is kind of lemon cat-ish. I see cat, I see lemon cat.
Let's do more identifying.
Okay, so what we're gonna do is we're gonna see our first kinds of graphs here. So let's take a peek. So
We're in the 80s.
let's look at this. First things first, on number 1, what shape is this one?
Circle.
It's a circle. What period length does the circle have again?
2 pi. Pi.
Okay.
2 pi.
I hear both.
Pi. 2 pi.
Now you just saying both.
She has so much energy.
Pi.
Our period length is pi.
That's what I said.
So what that means is we are going to put in our thetas, we need to pick them. We are going to take the angles we have, which are shockingly familiar angles, and we are going to go from 0 to pi.
Oh.
Those don't look familiar at all.
Yes, they do. Just saying. So we start at 0.
1.
No.
Think unit circle. What are our angles as we go around?
30, 25, 6.
Pi over 6.
In
Pi
radians.
Over 4.
Yup.
Pi over 3.
Pi over.
Pi over 3. 3 pi over 4.
Okay, take a breath. I know we're excited. She's got a different class right now. All right, our pi over 3, our pi over 2. That gets us all the way up to our halfway here. Then we're on our 2 pi over 3. Well, we're just picking our angles right now. So we're picking, so it's like picking x's to find y's. We're picking thetas to find our r.
Oh. So we're going to put it in there.
Mm-hmm.
Oh my gosh, it's so good.
3 pi over 4.
I'm so done.
5 pi over 6. And we're going to go all the way up to pi.
Just to pi?
Yep, the circle has a period length of pi. And so we go to pi. So we just, whatever the period length is, we go until there. That's where we stop. That's why we cared about the period length. I know you're going, that feels really random. We need it. All right, so then to find our R values, we go and take our pieces and substitute them in. Our R is going to equal -2 cosine of substituting each of our thetas.
But I put it in the wrong one.
Oh, use my calculator for this.
I was going to say, we can do these with unit circle values. We know them. We can also put them in the calculator to get decimals. We graph in things. We need lengths. So what is cosine of 0? Cosine of 0 is 1, which means -2 times 1
I got that
is
right.
-2.
Okay, never mind.
You just be making stuff up.
So
I said 1, and it's right, but it's...
-2.
Whoa. I thought. Never mind.
Thank you.
We're okay. So we're substituting all these pieces in. So we're going to do our R equals -2 cosine of pi over 6. Well, pi over 6 is one that we know. Cosine of pi over 6 is √3 over 2. So -2 times √3 over 2.
-2 root 2.
-2 √3 over 2. So we could, which was the same thing as -√3. We are graphing though. So -√3, while technically correct and lovely, what is that as a decimal?
0, 0, 0, 0, 0, 0, 0.
I mean, negative, yes. I was shaking my head no at the point 0, 0, 0s. -1.7. 1.7-ish.
Look, you did it.
So square root of, or negative square root of 3 is technically more accurate. However, not super helpful when it comes to graphing parts. We need decimals really, because remember that's our radius that we're looking for here. So we're gonna keep doing this. Pi over 4, same kind of deal. That's gonna be our -2 times our square root of 2 over 2.
Not what I got before.
Negative.
Wow.
Negative. So it would be -1.
All right, stop trying to do things in your brain. Write things down or put them in a calculator.
Wait, but we multiply pi over 4.
No, you're right.
Cosine of pi over 4. Cosine of pi over 4 means we have -2 times root 2 over 2. So we're at -√2, which again, we want to have as a decimal.
Negative 1.34.
As we say, -1.3536, somewhere around there.
I guess.
So it's -1.4 when we round technically.
Where am I going? -1, baby.
Then do our pi over 3. Because cosine of pi over 3 is is 1/2. So when we have our 1/2 times -2, we get -1.
See what?
And then we're going to keep going. We're going to fill in this table, continuing and doing the same thing. -2 cosine of pi over 2. Well, cosine of pi over 2 is 0, so that makes things easy. That's 0. And 2 pi over 3,
Negative.
positive 1.
1.4.
Positive 1.4,
2.
positive 1.7, and a positive 2. They're not always going to loop that nicely.
So it's just for circles?
I was going to say circles will loop nicely like that as long as we find the pattern. Don't just make the assumption when you get to the 0. Find your pattern. Make sure you found the proper loop.
If the 0 is in pi over 2, wouldn't it always be symmetrical?
Depends on which of the trig functions you have. It will be symmetrical. Just make sure you find at least a couple values to make sure you found the right symmetry. Because some of them are going to be on the x-axis, some are going to be on the y-axis. So double check yourself. But yes. So when we plot these up, we need to plot our points, and we have our r and our theta. So just like yesterday, we know our radius and our angle. So on angle 0, we have a radius -2. So angle 0, we're going to go not 1, 2 this way, but 1, 2 this way. 0, -2 is this point right there. That is chunky. Then we're going to have our pi over 6, so this angle, with our radius of -1.7. So we're going to go wrong way, slightly less than 2. So right there.
Wait. Oh, that makes sense.
Then we're going to have our pi over 4, which is this angle, -1.4. So somewhere there-ish, about the halfway mark. Then we have our pi over 3, this angle, -1. So wrong way through. Over there. And pi over 2 gets us to 0. We only got half our points up here yet. And then we have our 2 pi over 3. So we're at this angle here with our radius of 1. So we're going to be there. Our 3 pi over 4, which has a radius of 1.4. So about there. And then our 5 pi over 6 at 1.7 is right about there. And then when we're at pi, we're right back here. So it loops. And if I kept going, if I did my next piece, that 7 pi over 6, it would line up exactly with this guy. They would loop back around. So when we connect these up, it is really important. It's less important that we think it in this order on circles, but we can see it. When we connect up our dots, we need to connect them in order. So I need to connect my angle 0 to my pi over 6, to my pi over 4, to my pi over 3. Hang on a second, let me finish my thought, David. Then we've got our pi over 2, connects to this guy, connects to this guy, connects to this guy. So they connect up, but you have to go in order. Yes, sir.
What if it's a circle? Why does it matter if it's in order?
I was saying it doesn't particularly matter. Well, I mean, it does matter because we don't want to do this.
Well, I can't imagine, like,
So when we get into the next ones, we start getting some of those funky shapes. So think back to some of these funky things that I drew.
yeah.
It matters what order it is because we need to connect it so it makes these shapes not something chaotic.
All right.
So we connect pieces in the order of the angle. So you guys just made your first polar graph. You made a circle. Woohoo.
Testing on this?
Huh?
Are we testing on this?
Oh, absolutely not.
All right, okay, anyways.
We're making these. It'll go in as a quiz. So it'll help boost that quiz percent.
Oh, yeah.
Because some of us need a little boost in that quiz percent.
Oh, okay.
So it's gonna go in as a quiz and we'll, like, by the end of the week, you're gonna be making one of these things.
Ah. Oh, I'm so excited.
I know. All right. So let's do another one. Here's number 2. What shape is this?
A Limacon.
No, it is.
Mm-hmm. The Limacons.
Very nice.
Yeah. It's the lima bean.
Nuts.
Limacons have a period of 2 pi. So we need to go all the way around. So we're going to get all of our unit circle values. So this also lets us practice not only like our solving our trig functions, our unit circle stuff. So it really does make a lovely review anyway. So we start at 0. We're going to go all the way to 2 pi. So every place we have an angle, we want to write that up here. So we tend to give you guys graphs that look like the unit circle, so it's pieces we know. So if you look online, there are places that have these filled in, but it's totally fine. So we're going to do all of our unit circle values. So we're going to start with our pi over 6, and then we're going to do our pi over 4, and our pi over 3, and then our pi over 2. That gives us quadrant 1. Then we're going to have our 2 pi over 3, and our 3 pi over 4, and our 5 pi over 6 up to pi. That gives us quadrant 2. Then down into quadrant 3, we're at our 7 pi over 6, our 5 pi over 4, and our 4 pi over 3, getting us to our 3 pi over 2. That's quadrant 3. And then we get to our, 5 pi over 3. My brain got stuck there for a second. And then we're on our 7 pi over 4, 11 pi over 6, which loops us around to 2 pi. So that's all of our unit circle values.
But aren't the,
Because I'm good at counting when I plan boxes. Yes, dear. It should loop back around to be exactly what 0 is. I was like, I tend to put it there because it punctuates very well. But it doesn't really matter. It's going to be the same value. Because 0 and 2 pi mean the same thing. Huh?
Is there going to be a space on our worksheet as well?
I think so. All right.
Oh, okay.
So then we do the exact same thing. We're going to substitute our values in here. So 1 minus 2 times sine of 0. I was going to say, sine of 0 is 0. So 2 times 0 is 0. 1 minus 0 which is 1.
We're so good at math.
You mean she's good at
We're so good at
And then our pi over 6 is going to be 0.
calculator.
Yeah, we can use the calculators for these. I encourage us to use the calculators for these.
I encourage it too.
Mm-hmm. Negative 0.4 or negative 0.4. I know the boxes are small, but I was just trying to get everybody on the same kind of page. For pi over 3, yes, 0. Sorry, my brain got stuck there for a second. I heard 0.07, but I know that's not what you meant. The 1 minus the 2 sine of pi. So our sine of theta is pi over 4. Sine of pi over 4. Oh, no, sorry, pi over 6. Our sine of pi over 6, that's our 1/2. So 2 times the 1/2 gives us 1. 1 minus 1 gives us 0.
And I got 0.98.
Are you in degree mode or are you in radian mode?
I'm in degree mode.
That'd be
That's
why.
so funny.
Yep, if you're in the calculator, make sure you're in radian mode. Makes a difference. Everyone is wrong every now and then, so let's make sure we're realistic. So we've got our pi over 3, which is our negative 0.7. Our pi over 2, negative 1. Our 2 pi over 3, a negative 0.7. Our 3 pi over 4, negative 0.4. Our 5 pi over 6 is a 0. Have faith in ourselves. Just like don't try and look at the shape too hard when you're looking at values. We're looking at numbers right here. So what do we get for pi? 1. 7 pi over 6?
0.
No.
Maybe you need to look at.
Yes.
No.
Oh, wait.
Oh, it's 0.
No.
It's 2.
It's not. It's 2.
That's what I said.
Awesome. How about 5 pi over 4? 2.4. And then we're going to have, I'm going to fill this in because I want us to get to the shape before we get to the end. So our 4 pi over 3, we should get 2.7. Our 3 pi over 2, we should have as a 3. Our 5 pi over 3 should be 2.7. Our 7 pi over 4 should be our 2.4. 11 pi over 6 is going to be 2. And then 2 pi is going to be 1. And that should match our 0. So on things like this is where it really is going to make a difference that we connect pieces in order. Because this is kind of chaotically everywhere. So what I noticed right away is I noticed 2 sets of repetition. So this guy is 1 set, and this guy is another set that it's repeating again over here. So think of those as 2 separate pieces. When we plot these points up, just trying to get there. So we have our point 0, angle 0 with radius 1. Our first point's right there. Pi over 6, we're at angle 0. Pi over 4, so that's this center angle here. We have a radius at negative 0.4, so it's down. Sorry, you have to zoom it in. Right there. What's up? Aside from standing directly in front of the screen for everybody. Okay. So then we've got our pi over 3, negative 0.7. So we're on this angle at almost negative 1. So we're in there. I know, they're very small. Pi over 2, which is our straight up and down, at negative 1. So we're down here. And then it starts to kind of loop around on itself. Our 2 pi over 3 at negative 0.7 is right about there. And our 3 pi over 4 at negative 0.4 is right around there.
Why is your negative 0.4 farther from your negative 0.7? Oh, I didn't know if that was purposeful. I was just wondering if okay.
That better? We happier?
Thank you.
All right, so once we get back out to our 0, which then our next piece is our pi at 1, I'm going to connect these up. We started here, and then our very next piece was the 0. So before we get to that next line, we need to be at 0. Then we connect to our purple dot here, then to this green dot, then to the blue dot, pink, purple, green, out to purple. So that gives us this kind of lefty piece. Plotting these points up, very similar vibe. We need to have our pi of 1, which we got over here. 7 pi over 6, we have a radius of 2, so it's coming out way over here. 5 pi over 4, we're at 2.5, so this guy. Because we are on 7 pi over 6, that's this angle anyway. So if I had 7 pi over 6 with a negative 2, it would actually be up over here. So since it's over here, our positive 2 for 7 pi over 6 goes over this way. So then on our 5 pi over 4, oh, that is not what I meant. There we go. There we go. I'm at laser pointing. So for our 5 pi over 4, that's this guy over here. So we're out radius 1, 2.5-ish. 2.4. Okay, get to a little closer. 2.4. And then we have our 4 pi over 3. So on this angle, we're out at 2.7. So we're farther out. Our pi over 2, or 3 pi over 2, excuse me, we are at our 3. So down here. And then we've got our 5 pi over 3 giving us 2.7. Our 7 pi over 4 giving us 2.4. Our pi over 6 giving us 2. And then our 2 pi loops back around to 1. So when we connect these up, we get that thing. So we get this kind of loop-de-loop looking piece. It looks like this. Okay. So we will keep going with graphing stuff tomorrow. We'll get to our spiral and a couple other pieces. I'm going to put out on the little table right by the door so you can pick up the very, very, very lastest homework of the semester. Graphs.
Wait, is that what it is? Is that what it is?
It's very much the same thing. That is points from yesterday. So, like, it's due technically tomorrow, so I would give you guys 2 days because I know life happens. This will be due on Thursday. Because we're going to do more with it tomorrow. And then I'm giving us a time Google day in case we can never do. So, I'm going to put those over here for y'all. That's the last homework of the semester. Let me get to the page where I can read how to do that.
Lovely. You know what I like?
Staying quiet.
Oh, really? She does. I love that. You got one. Yep. Don't let her in.
I think I'm gonna read that book.
Oh, wait, you had to play last time.
be up there on the YouTube. It's I think it's a different playlist.
Yeah,
Okay.
you're right.
So if you got the link from the current page, it should be fine.